Alright, it has been over a week of this social distancing experiment, and while I do have stuff to do, like school and, stuff that should be done, I am getting a bit bored. So, while I was sitting in toilet, I was thinking, how does ray tracing work? And I found this paper from Thomas Möller Prosvia Clarus Ave. I have no idea how to pronounce those names. That's probably a company. Ben Trumbor. Yeah, I'm pretty much. Oh, these are the departments. Whoops. Anyways, after butchering those names, I checked this interesting little paper. It's quite a short one, yet very interesting. So it's all about ray triangle intersecting, and I thought maybe I should implement this. So I have Python here, and this is going to be a bit of a live coding, so sorry for that. Anyways, I'm going to do something. Yeah, new file. Sorry, this is only my second energy drink today, so untitled. Let's save this first. Data, programming stuff, Python. Let's have it named ray tracing. And let's have the file have the same name. So now we have our file. Now what do I think we have here? We have vectors, I think. Matrices. So quite the math heavy stuff. So I'm going to start with importing math, of course, as m, because I'm lazy and I don't like to write math all the time. Also, I'm probably going to be drawing it to a simple pyplot, so from matplotlib import pyplot as plt. Yes. And of course, I'm probably going to have to be using numpy, because while implementing your own matrix stuff is quite easy, it's a bit tedious and not really worth the time, especially in Python, where you have quite good matrix stuff in numpy. So import numpy as np. And I hate this ordering. So let's have numpy there, and now they're in a neat little order. So what we have here is basically, this is all what they are doing and how they are getting to their end result. So basically, and the implementation is also quite nice, but I'm not going to do it that way because that's more like C, and I'm trying to do it in more simple and Pythonic way to understand what's happening. This will not be probably as fast as, well, this will most definitely not be as fast as C, but also the implementation will probably be a bit slower because they reuse factors Q and P they calculate here. And I'm probably going to just have them calculated every time. So let's start with something like implementing this thing here. Or well, more specifically this, but we get there. So define, and the function should be something like ray triangle intersect though I think I'm going to do a bit copying and use this intersect triangle. Actually, it's much less to write. Anyways, I try not to use this too much because reasons. I want to understand this part. This is just implementation, and I'm trying to do it here. Anyways, we have our triangle, and what sort of variables will we need? Well, we are of course going to have the ray, and it will have origin, yes, and direction. I assume t is for time or how far we are in that direction, so it's scaling just a scalar. So okay, yeah, we're going to have as parameters O and D. So already an overdose of Corona news. Yay. Anyways, and triangle. I think we're going to have some vertices like here. So I'm actually going to have them first here. So V0, V1, and V2. And now, what do we have? This is mostly just how they arrive at their conclusion. So I'm mostly interested in this thing, because this will give us t, u, and v, where t is the distance, u is u, and v is v, and t is probably the same t as here, so it's the distance along the ray. So, what do we have? What do we need? We have E1, which is V1 minus V0, E2, which is V2 minus V0, and T, which is origin minus V0. So let's have those. So E1, E2, and T. And some equalities here. This shall be V1 minus V0. This will be V2 minus V0, I think. Yes. And this will be O. No. I'm always pressing 0 when I have to press O. And with shift, it comes as equality sign. How many times I'm going to do that in this one simple project? Or I hope it's a simple project. And I hope I won't do that too many times. Okay, origin minus V0. Okay, next thing we have here is D cross E dot E. Oh, E2 and E1, okay. And they define P as D cross E2 and Q T cross E1. So let's have P equal numpy cross, and we will have D and E2. And then we will have Q. Oh, and just for sake of having these things on the same row or column. Anyways, numpy dot cross. We will have T E1. Okay, now we, I think, have everything we need. So we will have something like this TUV vector. So let's calculate that. TUV equals And then we will have some sort of scaling factor, 1 over numpy dot and p and e1. And yes, then we will have it times, and because of the direction here, I'm going to do something like transposing stuff. So we will do it in numpy.transpose, and we will have an array. And that array shall contain stuff q times q.e, p.t, q.d. Right, so q, concentrate, so numpy dot. We're gonna have 3 dot products, so I'm gonna copy this 3 times because I'm lazy. And then what shall we have? Q and E2, P and T, Q and D. I hope I remembered to name these correctly. They are inside this array, and I think that's good enough for now. I hope. I really hope. So let's just return that. And now, well, let's just test. No clear errors anywhere, so let's try to define something. Let's have v0, v1, and v2. They shall be some sort of points of type np array. And what does this np array now will contain? It will contain our triangle points. Simple triangle should be something like minus 0.5, which is the x. This is the lower corner. Minus 0.5, which is the y value. And then let's have it just 1. It's a bit further from the origin. And let's copy that. Then we will have the top corner, which would be something like on the x-axis it will be 0. On y-axis it will be 0.5. Let's have it like that. And still at the same depth. And finally we will have this, but where our x is positive 0.5. So I think we have now our triangle vertices defined. And what else will we need? We will need a origin. Let's just copy this, because origin will be simply just the origin. Oh, and 0.0.0. So this is our origin, where our camera is located. And then the direction shall be something akin to this. The only thing is that we will be pointing it towards the z direction. And now let's just check what we will get if we try this intersect triangle thing here. let's have it return to a value, which is now just something like the return. Let's run it, and R is array, and it, well, this is easy to check. This is the length or distance. It's 1 because of this last element here, and the rest here is barycentric coordinates, but they do look like they are between 1 and 0 both, and their sum is also between 1 and 0, which would seem it's inside the triangle. And then if we change our direction to be something like also 1, 1 in the XY direction, so it's definitely not going to be hitting that triangle. Let's run it and check it. So yes, this is most definitely not in between 0 and 1, and their sum is most definitely also not between 0 and 1. Though the distance is still same, but it's irrelevant in this case. All right. So I think this triangle intersection stuff works. Now the next thing is to actually do the ray tracing. So now we have this implemented, and the rest is pretty much just doing some basic stuff. So okay, we will have our ray trace, which is our, basically we will have our screen here, or this will output our screen buffer of sorts. And then what sort of variables are we going to need? Well, we are of course going to need our triangle vertices, v0, v1, and v2. If this were a scene of multiple triangles, we would just have to choose another way of representing all of our triangles, but this is for one triangle only, just to see if this works. So this is the simplest most case I could think of. Alright, so basically now, if we have those, yes, actually, well, I'm gonna define these here. They are not that important. So origin shall be basically, actually I'm going to copy this. This is because whatever I'm going to later maybe do with the triangle, transforming it, scaling, rotating, I will do it in a way that it will rotate it around the origin, etc., like in your normal day-to-day 3D programming, because that's the easiest thing I know. Of course, now that we have this origin and direction, we could technically point the camera any way we want, but that's just not very easy, and you know, to incorporate in your normal raster style of rendering. So we need our origin, and then what else do we need? Well, we will need a resolution because it's a raster array of sorts. So resolution along x-axis, which is 100, resolution against y-axis. Now these could be different, but in this case, because I'm going to be using the same field of view, because it's basically a square, so field of view shall be m dot pi over 2. So it's going to be basically 45, sorry, it will be 90 degrees field of view. So yes, let's have these a bit prettier, somewhere where they're nice, like this. Now we have our resolution, field of view, and origin defined. Actually, I'm going to reorder these because it's much nicer. So we have our resolution, And field of view defined origin will be there. We are also going to need the well, it's a bit hard to explain, but what I am going to do is basically have it something like this, and now we'll just flip it. Alright, so here's our top-down view from the camera. And because we are going to be basically tracing the ray along this line, we will have to find basically how much for each pixel we will be moving in basically this direction. It could be any direction because I haven't defined the coordinate system, but anyways, let's assume we will be moving from around here all the way to here, and that means we will need to have this distance and divide it with equal segments. And this is fairly easy. We will just need the whole length here, and to find that we will basically do something simple as having this line, and this screen will be unit length away from the origin. So this will be something like 1. And pardon my paint skills here. Alright, so this is 1. So basically in that case, this will be basically tangent of the angle that is here. Let's have it somewhat nicely here, yes. So basically tangent of this angle is this divided by this, but this is 1, so it's going to end up being this. Simple enough. So how do we implement it? It's simple. We are going to ask Python to compute our tangent. So we will have A, which is going to be m for math dot tangent of field of view. And of course, pi over 2 will be something akin to infinity, which is not what we want. And also pi over 2 is this whole, both triangles, angles summed. So we will just divide it by 2, which will be pretty much pi over 4, which would give us something like 1. Yes, because this is going to end up being a one of those basic triangles where the catheti are of length 1, and this will be length square root of 2, but that's not important in this case. And this is our length of up until this point, but we will need to multiply it by 2 because there are 2 triangles. Okay, and we will do the same for our y resolution or whatever. So this is going to be, let's say, b. So we will have our basically a, and this is our b, but in lowercase. Sorry. This is a, and if we rotate it 90 degrees, whatever, we don't need paint for this. So okay, we have a and b. Both are same because the field of view I'm using for both is the same, but that would change. We would have something like fov a and fov b if we would have something not square. But in this case, for simplicity's sake, let's have it that way. But just know that there's the possibility of later changing that. All right, then we will have, of course, our screen, which will be just a simple array. And I think this is all we're going to need for this. Or maybe I should rename these A and B. So this shall be horizontal and this shall be vertical length of the screen. Now we will need a loop. So for I in range resolution y, this is because the arrays work in not xy but yx way. And for j in range res x. And now we will, of course, okay, this is interesting. Now they're in the same indentation level. So we'll have our row here, which is also an empty array. And then for j in range resolution of x, we will need to calculate the direction, d vector, which in this case we did manually, but we want to, that to basically change with the screen. So this shall be numpy array. It will be of some sort of array. Like this. And then what shall we have as inputs in there? So the first, or x1, shall be something like this. We're going to scale it, j divided by resolution over x times the horizontal length. And then we will subtract from that the horizontal length divided by 2. That will make it so that the center point will be at 0. Alright, and then we will have the same, but for y. So I divided by resolution over y. And these are going to be the vertical stuff. So basically the same. And z, let's have it just be 1, because that's not that important. And then we will have our intersection. Which shall be intersect triangle here. And we don't even have to change our variable names, which is nice. Might not be good, but nice in this case. And then we will have our u and v, which we will extract from the intersection. So these shall be intersection. And because of this order here, t is the 0th index, u is first, and v is second, so 1 and 2. And now we will need to check that this is actually inside the triangle, because as we saw earlier, this only gives us this vector, which itself just doesn't tell us. Or it tells us, but not straight away. So we need a check. So we need to check that if u is smaller or equal to 1 and u is greater or equal to 0. Actually, I want this the other way around. So from 0 to u has to be from 0 to 1. And basically the same thing, but for v. And lastly, the same thing, but for u plus v. Like this. Now I'm going to add some parentheses to help seeing what parts are doing what. Basically, these aren't necessary, but I like to have many parentheses rather than too few. Alright, now we know that we are inside the triangle. So let's just return. No, we're not going to return. We're going to append row.append, and we're going to append a tuple of 1, 1, 1. So red, green, and blue channels, or all at full force, so it's going to be white. And then else row.append a tuple of 0, 0, 0, which is basically black. And then we will have it screen.append row, and then we will return that screen. Basically, that's like a screen buffer. We're not going to need this anymore. So we'll have our screen, which is going to be this ray trace. And let's see if this even runs. Did I do? Yeah, too many mistakes. I forgot the commas here. Okay, looks like it's running. And is it numpy.shape? And we will have screen in there. It should be 100 by 100. Yes, and tuples of 3. So yes. Now we will actually plot what we have. So we will create figure. Fg is plt.figure. And we need the assignment. Then we will have our x, which is fg.gca. Just your standard setup of stuff. Then we will have our plot, which will be ax.imshow of the screen and origin equals lower, because by default the y-axis is flipped in a way that it's not very easy to see what's happening. Alright, and finally we will just call plt.draw and plt.pause, and we'll pause for 1e minus 3, so 1,000th of a second, I think. So now that we have those things done, we should have a plot of some sort. Well, of some sort, yes. And there is 1, and there's 0. So yeah, we have something, but it didn't plot it correctly. So let's see. We have our row where we append something, yes, zeros and ones, and maybe it's just too low. Let's try 255. I don't remember how this likes stuff. Oh yes, here we have our ray traced triangle. So all right. Oh, maybe it's because, yes, let's try one more thing. It might be because these are all integers, but if I put point zeros in there, they should become floats. And it might require us to use floats. Let's see what happens. Yes, so basically having those as floats. Now, the next thing I'd like to have is some color. You know, there's this basic... whenever you do the first tutorials on 3D stuff, you will have this white triangle stuff. And you will have those fragment shaders and vertex shaders, etc. So we're going to basically do something like the fragment shader. So now we know that we have u and v values. We also can have w, which is 1 minus u plus v, if I remember correctly. And now we can have, we can use these to calculate our position in the triangle and use those to influence how much we use color. So from barycentric to basically color, let's do something fun. Let's first have our couple of tabs here because of reasons. So let's have the first value here be something like 1 times, and this is just scaling. If it would be somewhere like in between 0 and 255, it would be 255. So this is just a scaling factor. Then we will have our 1 minus u plus v, and we will do this basically for every row here, but we will change the u and v. So first we will have the u and v. This is our red channel. Then we will have our w plus u, and then we will have our w plus v. So I think this should give us some nice color, and of course we need to remember the commas. Let's see what happens if I run this. Oh yes, we have our nice little red corner is the first one. Then we will have our green corner here, w plus u, and our blue corner, which is w plus v. So basically the edges. All right, I think this is a good place for me to stop. So how to proceed from here on forward in this complete rendering sense, we would have to encapsulate these vertices into basically an array of some sort, and then we would check, we would color based on how close, so basically the t intersections index 0. We would use that to basically check whether or not the triangle we intersected is the closest one, and we would have to do for each and every triangle. And most probably the thing that would need to be done is to order those triangles in a way of some sort, maybe to make it faster. But anyways, for sake of one triangle, this is exactly what's needed. So, well, this didn't alleviate my boredom too much, but at least I got a pretty triangle. So, thank you if you managed to watch this far, and hope the corona won't get you. See ya.